project and then an example using off-grid electrical system and as well as future houses. And I'm going to close it out with summary. Right. First, why DC? I'm going to try to explain the reasons, several reasons why DC. Very first one is the increasing numbers and uses of residential DC loads. That's one of the main things that we have witnessed in the past decade or so, right? How many of you, have a smartphone right now? I would say every single one, right? Maybe more than one, right? And every smartphone, right? Inside the smartphones, right? The electrical systems or the electronic system inside the phone is running on DC. When you charge the phone to the wall, right, it's actually charging a battery, and that is operating in DC, right? So smartphones is a good representation of DC load that has become very prevalent these days, right? And as you can see, the number of smartphones, this is all the way to 2021, the number is staggering, right? It's 2 billion units of smartphones in the world, right? Another example of a good DC load that we've seen more and more these days is the LED lights, right? So, DC, you'll be at a disadvantage if you are not using LED lights. And as we know, LED lights runs on DC, even though you plug it into AC system, but internally it works on DC. Same thing with tablets, and you can see the increase in the number of LED lights, as well as the cost that keeps coming down, getting cheaper, so more people can afford, right? And the same thing with tablets. Point is, right, the number of DC loads in our house will be increasing, and will keep increasing. Now, if you look at just one device, yeah, the power is not that big, right? If, let's say, this is on the low side. Let's just say that every smartphone, you charge it with USB. And let's say on average, USB is 5 volt and drawing 1 amp. And you charge it for 1 hour. And then there are 2 billions in the world. If you look at just 5 times 1 times 1, that's not bad at all. But if you multiply it by the number of the units around the globe, look at the number there. It becomes huge, right? 10 gigawatt hour of energy being used by just smartphone. Imagine, LEDs, tablets, and guess what? This energy is being processed through DC internally. Right? That's one reason. Another reason, we've been seeing also this technology that has been, fastly developing is called USB Type-C. Right, more and more laptops, smartphones are, running or having the interface with USB Type-C. And as a power person, somebody whose background's in power, I'm more interested in one of the features of USB-C. There are many features, great features, but one of the things that caught my eyes is this one right there. That in the future, the target power of USB is 100 watts. Right now, it's not much. Right now, it's probably around 20, 25 watts. But imagine if USB-C can deliver 100 watts. Can you imagine how many DC loads it can handle? Right? If that's the case, then we don't really need AC wall plug, for example, to power TV, to power laptop, and so on and so forth. Right? And here's some statistic that I ran a few years ago. In the US, of course, here we see the mix, right? A percentage of AC loads and DC loads in our house in the US on average or typical house. Mostly TV, laptops, and desktops, those are DC. And you can see the percentage is about 20% back in 2000. Fast forward to 2018, you can see the percent is increasing to 30%. And I would predict that this number, the percentage of DC, is actually higher in developing countries, right? Why? Reason why in the US the AC load is has a big percentage, because here, if you've been to the US, you can see that our fridge is big, right? Washing machine is big, air conditioning is big, right? So everything is big. So these are all big AC loads. Whereas in Indonesia, for example, right, fridge is smaller, right, and washing machine is smaller. And so I would, I would guess that the mix of DC is higher in developing countries. I would argue that. Right? And so, what's the big deal about these DC loads? Well, this is the problem that we're having right now that we need to address. Right, as soon as you have more and more DC loads in our house, we gotta find a way to be able to convert, right, the electricity from AC, which is the wall plug that's coming from PLN, for example, to DC, which is our load, right? So in the process, you're gonna need this converter, AC to DC. Unfortunately, this converter produces loss between 17 to 35% loss, and this loss accumulates, right, over the year, over lifetime, right? It's gonna accumulate, and that corresponds to cost, basically, right? So there's a problem there, a mismatching problem. Now, again, if you just look at one device, the number is not that bad. But notice that if, let's say, the loss, right, before I put 17 to 35% loss, let's just say that the loss is not that big. Let's just say that the loss is only 5%, not big, right? Maybe you're thinking, that's not a big deal, 5%. Take a look at what happens if that 5% comes from so many of these DC loads, right? Globally, right? We look at the big picture. Then if let's say that a tablet, right, consumes on average 12 kilowatt hour per year, and there's 760 million tablets in 2016, do the math, right? You multiply this and you got energy being used, and then 5% of that is a loss, right? And that becomes, look, 480 gigawatt hour per year. That 5% from one device, not big, but when you put 760 million devices, that becomes 480 gigawatt hour per year. Same thing with smartphone. And I'm only putting two examples. There's more, but from these two examples, if you add them up, like the 5% loss represents 12 units of 10 megawatt power plants operating 24 by 7 for the entire year. Now we're not talking small anymore, right? When the amount of loss is comparable to having 12 power plants, that's not small, right? And moving on, solar panels is another DC source that has become very popular the past 10 years or so. And as we know, solar panels puts out DC. So now if we have a source that's DC, loads that are also DC, then the most logical way is to convert from DC to DC. What we have right now is, as some of you know, from the solar panel, we invert it to AC, right? To be able to be connected to our house. And then right at the point of connection to the loads, we convert that AC back to DC, and then another DC to DC. In the process, you're going to have more losses, right? Not good. Right? Very lossy, it's not efficient. So, and then another reason why DC have to do with renewable energy, right? Ironically, areas that have a lot of potentials for renewable energy, unfortunately, for now, they have not tapped into these energy sources, in the optimum way. So we can help by, developing technology that can improve utilization of these energy sources, small or big, right? And you can see here's a picture of Indonesian islands, right? You can see most of the islands are still dark. So we need to be able to develop technology that could help increase access of electricity through renewable energy. So the point is, if I could put one smile on this kid's face, that would make my day. And that could be done, for example, through the technology that I've developed since 2010. Right? All right, so when it comes to residential DC electricity, DC House has been initiated in 2010. It's called DC House Project. And the initial goal is to develop alternative solution to existing rural electrification technologies, which is using directly DC electricity with DC loads. So no intermediate AC. And thereby providing seamless integration of one or more small scale. So the focus here is small scale, not big scale renewable energy sources, right? We've already have technologies that make use of big scale renewable energy, such as wind farm, hydropower, micro hydro, wind farm or solar farm, sorry. But many of the sources are small scale. And it's too bad that we are not using those in the most optimum way, right? A lot of waste, right, of not being able to use. So it's too bad. So that's why we can improve this by having an alternative solution to be able to utilize those. And it's a bottom-up approach to rural electrification. So on a small scale, it could be a solar lighting box, as simple as solar lighting box. Residential scale, it could be a standalone of the grid house, and then on a bigger scale, it could be a network of DC houses. And when it comes to, again, rural electrification, the alternate solution of rural electrification, my philosophy is that one size doesn't fit all, right? For some regions, yes, micro hydro might fit in very well, but for some others who do not have, big rivers, they only have small water streams, then maybe we need alternative technology such as DC house to help them tap that small energy sources, right? So I'm not going to go over these features, but there's different features of DC house. Simplified diagram of the DC house project. You can see the three components of the project. You have the generation side on the left, then you have the interface component in the middle, and you have the loads itself on the right. And these are all DC. And key technology is how can we combine small scale, not big scale, small, right? Watts, tens of watts, small but many. Combine the energy into one single DC bus, and that sounds easy, right? But it's not. Trust me. And you combine them using this converter that I call miso, like a miso soup, like the Japanese miso soup. But miso stands for multiple input, single output, right? And that's feeding into our DC house. They are run all on DC, strictly DC, no AC. And so recent status, we developed the technology since 2010 on all three sides, right? You have the generation, interface, and loads. On the generation side, there are many ideas, and the audience, feel free if you're interested to contribute to this effort, right? The key word here is small scale. I'm not really interested in big scale. That's already done. I'm interested in low scale, small scale, such as this technology, right? I had this idea a long time ago, but then some people in the Europe, they already built this or make this as a product where you have this portable nano hydro, you can say. You can put it in a pocket, and then as soon as you see a small water stream, you can just dip it into the water and it creates electricity, right? Small, but if you combine many, it becomes big, right? Same thing with this play park generator. So we've developed this at Cal Poly, right? Kids can play the swing, can play the seesaw, they can play the merry-go-round, and in the process, we could generate power, and we already proven that this works at Cal Poly. Not much, but still works, right? Still generates some energy. And so many things that you can do with DC House in terms of research, if you're interested in participating in the research on DC House. This is the energy management portion of this. I'm not going to go through this in details, but you need a brain basically to be able to coordinate between energy being used, energy being produced, and energy being stored, right? Quickly, another recent status is that, remember the MISO, the key technology, right? That's the key technology. You have to be able to combine smaller sources into one. And alhamdulillah, after like several years, maybe 7 years, we found a key to the solution, and I received a US patent on this technology right there. Right? So I was a celebrity for a short moment. That is in a local newspaper and local news. Right? So that's MISO. And there's more, right? Sky's the limit. There's so many things. Pretty much a new field to explore is DC, right? Things like smart wall plug. I'll tell you about it briefly. And then DC protection circuit, because it is a challenge to be able to protect DC than AC, because DC is always high. Doesn't, it's not like AC, it fluctuates, it goes to zero crossing, right? So it is challenging. And so we developed, or we've attempted to develop some technologies related to that as well. Quickly, this is the smart wall plug. What it is that one problem with DC loads is that they are not standardized. Unlike AC, right? In Indonesia, you buy AC appliance, they're all standard, right? 220 volt AC RMS. But when it comes to DC, it's all over the place, right? Some DC load is 12 volts, other DC load is 24, another one is 5 volts. So if that's the case, are you going to provide multiple wall plugs? No way, right? That's going to be confusing. So how do we do this? We can provide one simple plug, but there is that plug is going to be smart, meaning whatever load you plug in, if that load requires 9 volts, then the brain behind that wall plug will be able to determine, hey, I'm going to output 9 volts as well. So smart DC wall plug. So we attempted this 3 times. I'm still not happy. So there's still things to develop here as well. DC grid with distributed renewables, that would be DC house network. That would be useful for example, in Indonesia, we have villages that has clusters of houses like this, right? These are pictures from Indonesia, some villages in parts of Indonesia. So you can see if the houses are close by, forming a cluster, it would be nice to be able to network, right, the DC house here. And here's the picture of it right there. So every single house can exchange power, right? That's DC centralized DC bus. Every single house is DC house. And here's the comparison between conventional technology, micro hydro, solar farm, wind farm, and so on, compared to the DC house solution that I'm offering. You can see that if, for example, I'm not saying that this solution on the left is bad. I'm just saying that one size doesn't fit all, right? And if you use DC house, my claim is that it is more reliable, right? For example, here on the left with the conventional technology, if the source, which is a big source, is down, then the entire village is down or blackout. Here, right, if one source right there is down, then everything else is still on, and this house is still on as well because it can get its energy from its neighbor, right? And so on and so forth. There's more to it, but since we are time limited, I'm going to skip ahead. Another example of how we can apply or implement DC house system is for future house. I would envision that in the future, residential houses, will be running 2 different electricity, AC and DC. Again, why? Because of the increase of numbers of DC loads. So you have 2 different paths, basically, right? You have AC from the utility or PLN, and you have DC from solar panels. So if you have DC loads, right, you're going to go straight from solar panels to DC loads. If you have AC loads, you're going to go straight from the utility to AC loads. If utility is down, then you can support the energy of the AC loads through this path right here, inverter. So crisscrossing the path. The same way, if the solar panel is down for nighttime, then the DC load could be power from the PLN, right? So crisscrossing. So this is what I call hybrid AC/DC urban house or just house. And I'm going to skip this one, net zero building, and I'm going to show you what do you call it, prototypes that we have so far for DC house. We have one at Cal Poly, we have one at Pajajaran University, and Philippines is actually the first country who was interested in DC house, believe it or not. Indonesia came later. So I was invited to Philippines for 1 month to build a DC house on their campus, and now they're doing some projects, using DC house there. So I'm very glad that they, do this. And then here's an example of mixing or hybriding small scale wind and small scale solar into this office in Jatinangor Regency office. So it's still there. But those are the examples of prototypes. I'm hoping that more and more universities in Indonesia is interested in, having prototype on their campus. And there's still a lot to develop. As I said, I need more help. So the more help I get, the better. Right? This is not a single person effort. It's a group effort, right? Global effort too. It's not just for Indonesia. It's for other countries as well who are in need of having access to electricity from small sources. And as a summary, residential DC loads will become increasingly prevalent in types and capacity, and coupled with increasing use of PVs, the need for developing residential DC electrical system to facilitate the efficient use of DC sources become crucial. Residential DC electrical system offers an alternate solution to rural electrification and lays down the necessary platform for future hybrid AC-DC house. And still a lot to explore, but then I'm listing software because some people say, oh, these are all hardware. No, they're also software that you can help. And I'm listing 3 examples here. I'm not going to read them through, but hopefully you get the copy of the presentation sometime and you can see this by yourselves. And references. And finally, that would conclude my presentation. Hopefully that gives you some basic understanding of what I'm trying to do with DC House project. If you're interested, we have a DC House website, and there's the info that you can reach out. If you have any questions on DC House. With that, I'm going to close my presentation. Thank you again for the opportunity. Billahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor Taufik. That's a very wonderful ideas. You explained about the opportunities to improve electrical systems performance and efficiency by doing the DC house. It's very interesting. And I hope the audience will ask you about something that you have already explained. And the audience can give or can send the questions to the chat room by writing down TF underscore your name and then underscore your institution and underscore your questions. I will be read out the question for Professor Taufik later on at the end of the session. Thank you again for Professor Taufik for your presentation. And the next presenter will be Associate Professor Dr. Oki Muraza. Dr. Oki, are you ready? Okay. I think there's a misunderstanding this. For the second presenter would be Professor Dr.